Hi, let's talk about time value of money today, right? That's the topic of chapter 4. It actually lays down some very fundamental basics or uh, tools that we're going to be using um, in the class, in this class and some others, but you may already have come across the concept of time value of money. If not, I'm not going to assume any prior knowledge. We'll start from scratch. So, what is time value of money? Well, we're going to continue with the same approach as we had in the previous chapter. We're going to pose a question and start to answer those, and that's how these lectures are going to be structured. All right, so let's get started. We have heard countless times that time is money, referring to the fact that our time is valuable. But what is time value of money? Explain to Mr. Scratch My Head. So, talking about, well, how do we define time value of money? Time value of money actually um, is a notion that apart from the amount of money, the timing of when that cash flow is received or paid, the timing also has some value, right? Um, so if we're talking about, most people say, do you, I'm going to pay you $100. Do you want it now or a year later? And most people will say, well, give it to me now, right? On the other hand, if you say, um, you need to pay me $100, do you want to pay it to me now or later? And most people would say, well, I'll pay it later, right? And the reason is that we prefer receiving cash flows earlier than later and paying cash flows later than earlier. Why is that? Well, a very simple answer is that there is such a thing as interest, right? So the biggest reason for such a preference is the opportunity cost. Well, not having money in your possession versus having money in your possession. There is an opportunity cost for not having money in your possession. Um, because you want, if you needed it, you won't have it with you. Um, the inflation, well, $100. If you were going to receive $100 next year instead of today, well, it may actually buy you less things, right? And of course, risk. I promise to pay you $100, um, and I can give it to you today or say next year. Well, if we waited till next year, who knows what? I might change my mind. I might move away. I might be dead for many reasons, right? That's a risky endeavor, waiting uh, to receive cash flow. So these factors will determine the amount of interest charged on a loan. So we mentioned the term interest rates, right? But interest rates reflect these three factors: opportunity cost, inflation, and risk, right? So if if you gave me the $100 today and I put it in the bank, I'll have more than $100 a year later. So that itself makes it um, not worthwhile to wait a year to receive the 100, right? So that's the time value of money. It's the notion that the timing of cash flows matter. So let's see what happens. So let's say you have something in your hand today. We call it present value, right? And denote it with PV, right? Um, and the interest rate that is able to obtain or have to pay is I percent per year. So in the notations we're going to be using, typically, small letter like an I here is going to refer to a rate. So, and um, and of course, capitalized PV refers to an amount, right? So what happens after a year? Well, if you put it in the bank which pays you I per year, let's say 5%, right? And you put in $100. So if $100, if the PV is $100 and I is 5%, what we're saying is that after 1 year, you're going to have your original $100 in the bank and 5% of $100 on top of that, right? So 100 times 0.05, 5% in decimals 0.05. 100 times 0.05, that's the interest in dollars you will have earned. And you have your original $100, right? So it's PV plus PV times I. Or you take the common factor out, PV times 1 plus I, right? And so that's, and what that is how much we'll have a year later, and we call it future value, FV. But future value, can be, we have to be more specific than just saying future value, because the future, a year from now is the future, 2 years from now is the future, 10 years from now is the future, right? So when we say future value, we use a subscript like 1 here. That's future value after 1 year, right? Of course, present value is right now. In terms of time periods, we would say 0. If we were going to put a subscript, we would put a subscript of 0, but there's no need for that, because present value is always at the point of time, which is right now, right? So we don't have to say when, the present value when. Anyways, so basically that's the future value after 1 year, right? It's PV times 1 plus I. Well, what if we waited another year? If we waited another year, well, the entire amount we have in the bank, which is FV1 after the first year, will earn interest during the second year. So it's going to be FV2, future value after 2 years, is future value after the first year, times 1 plus I, right? And of course, we know that FV1 was PV times 1 plus I. So if we put that value in for FV1 here, we get PV times 1 plus I, all of that times 1 plus I again. And so it's present value times 1 plus I raised to the power of 2, or squared, right? Because we simply take the present value and multiply it with 1 plus I 2 times. And likewise, FV3 is going to be FV2 times 1 plus I. And FV2 was PV times 1 plus I squared, and multiplied with 1 plus I again. So FV3, future value after 3 years, would be present value times 1 plus I raised to the power of 3, or cubed. And so you can see a general trend emerging. We wanted to get the future value after n number of years. It would simply be present value multiplied with 1 plus I raised to the power of n, right? So this is the simplest TVM equation, where future value of a given cash flow in the present value, equals that present value times 1 plus I raised to the power of n. So we have 4 variables. We have FV, we have PV, we have I, and we have n, right? And many basic TVM problems will give you 3 of these, and you have to find out what the 4th is, the 4th item. So it's just interpreting the words properly in a word problem. So to solve those basic problems, you need to find out what is given, and then find what they'll ask you for, right? So you identify what is given, and then identify what's being asked for. And then you can use this basic formula. You plug in the 3 things you know and find the value of the 4th. And for that, you may need to do a little bit of algebraic manipulation, but we even take that out of the equation when we bring in a financial calculator. You won't even need to know the algebra. Anyways, so let's solve some problems. When Jeremiah's cow Betsy was dying, he promised her that he would ensure that her calf Kelsey leads a comfortable life. As a result, he has decided to build an air-conditioned shed for Kelsey at a cost of $1,500. Jeremiah's friend Brigham agrees to extend a 5-year loan at a low interest rate of 4% per year. How much will Jeremiah owe 5 years later? Okay, so what's given here? We know that Jeremiah needs $1,500 right now, right? And so that's the present value. We got interest rate given to us 4% and number of years 5 years, so we want to find out the future value after 5 years, FV5. Okay, so we got the present value, we have the interest rate 4% and number of years 5. What do we need to find out? FV5, future value after 5 years. Okay, so to calculate this answer, we just have to take the present value, 1,500, multiply it with 1 plus I. I is interest rate, so in decimal form it'll be 4% will be 0.04, and we raise it to the power of n. So 1.04, 1 plus 0.04 is 1.04. Raise that to the power of 5 and multiply it with 1,500, and you get 1824.98, right? So let's go to the calculator, right? And once again, the calculator I have here on the screen, the one I'll be showing you how to work with is the Texas Instruments BA2 Plus calculator. This is the professional version, but you don't need to get the professional version. Just the BA2 Plus has all these keys and will be sufficient for the class, right? All right, so to use a calculator, you first turn it on. That's the on-off button. We got 1,500 as the present value. Oh, let me clear it because there's a clear button at the bottom here whenever you want to clear it. I started with 1,500, but actually, given that the sequence of operations, we should do the power first before the multiplication. So 1 plus 0.04 is 1.04. 1.04, right? And then I'm going to use the y to the power x button right above number 9. Y to the power x, 5, press 5, then equal to, then multiply it with $1,500. And then equals, and we get the answer 1824.979 or 1824.98. That's the answer, right? Now, I'll show you how we can do it using the TVM keys, the time value of money keys, in this calculator. And before we do that, let me clear that screen. But before we do that, we have to clear the TVM worksheet. And so if you see just above the FV button, there's a CLR TVM, clear TVM button, right? And what you need to do is to access CLR TVM, and that stands for Clear Time Value of Money Worksheet, right? So to access that, you must push the second key here, the first key in the second row, which is second, and then FV, and we just cleared TVM. So it clears anything that's in the memory from a prior calculation for time value of money, but you can start to recognize these keys, right? So in this particular case, we're going to say 1500 is the present value, so 1500 PV. 4% was the interest, and the calculator knows that when you say 4 is I above I, that that it is the interest rate, right? And interest rate is 4. Then 5 was N, and now we just say compute up on top FV. We're finding FV, and we get the answer 1824.979, the same answer as we had before, but one thing you will notice that the answer came out as a negative number, right? Because the time value of money worksheet actually keeps tabs of the symbol. In other words, it says if you receive 1500 today and we put that in as a positive cash flow, then you must pay out 1824.98 5 years later. So that's your original principal plus 5 years of interest that you're going to have to pay back, and then that payout becomes a negative cash flow, right? So receiving cash flows that you receive are positive, cash flows that you pay out are negative, and the TVM worksheet actually is keeping you honest about that. All right, let's go to let's go to the next problem, right? Cedar leaves grow at a compounded rate of 16% per month. You need 3,803 leaves to make a nice thatch roof over your pet raccoon's head before winter approaches in approximately 9 months. How many leaves must your cedar tree currently possess to keep your raccoon from freezing in the winter? Right? Well, what do we have in this case? Well, it's not. It doesn't use dollars, just number of leaves, and there's no rate of interest, but rather rate of growth. But the notions that we apply are similar. We need to find out, in order to have 3,803 leaves in the future, well, that would be future value, right? 16% per month is the rate of growth, which is the equivalent of interest rate. And 9 months is how much time you have, 9 months. So N is 9. And we have to make sure that the periodicity matters. They match. Like it's not 16% per year, and 9 months, we wouldn't be able to just use 16 and 9, right? But the growth rate is 16% per month, and the number of months is 9. So they match, the periods match, and so we can simply plug that in. If they didn't, we would have to make some adjustments, and we'll talk about that in future problems. All right, so we got the FV after 9 months, FV, we have I, we have N, and we got to find the present value, the PV, right? And so just like FVN was PV times 1 plus I raised to the power of N, from that formula, if we divided both sides with 1 plus I raised to the power of N, we'll get this expression for PV, so, which is FV divided by 1 plus I raised to the power of N. And so if we did that, we're going to get 1,000 leaves, right? I go over to the calculator, I do second, and FV, clear TVM. By the way, I hope you can see the calculator. I tried to make it bigger, but this teaching tool I have only has one size of a calculator that comes up on the screen. But I've adjusted the the screen resolution somewhat, so it's bigger than it was originally, but that's about where we are. I hope you can see it. Anyways, if not, I have put all these instructions at the bottom of each slide and how you can do it. But right now, we did second FE to clear TVM worksheet, and actually I wanted to clear the screen also, because we'll do this algebra first, where we simply did 1.06, so 1 plus 0.16 or 1.16, right? So we're going to do 1.16 y to the power x 9 equals, and that's the most complex operation. I want to do that before, right? And then there's a 1 over x button. Just before y to the power x is 1 over x. So I got the reciprocal of that, and now I simply will need to multiply this value with 3803. 3803. The answer is 1000.010183, but so 1000 at least. Basically, that's what we need. If we want to use the TVM worksheet, we do second FV cleared, we do 3803 as FV, 16 as I, 9 as N, and say compute PV. Right, we get the answer. So you can already start to see the benefits of having a financial calculator. The other way that we proceeded, you can do it with any calculator, scientific calculator as well. Not a 4-function calculator, because it won't let you raise to the power of 9. But any scientific calculator would also work. But the financial calculator functions actually make this very simple. And you'll see as we go along that we start to do more complicated calculations. And then the benefit of having a financial calculator is really startling. Okay, so I'm going to clear this and be ready for the next problem, right? So far, remember this original formula had FV, PV, I, and N, and so far we've had a missing PV and a missing FV, right? Now, of course, we'll have 2 other things left, so we'll have problems that tackle a missing I and a missing N. All right, so let's look at this problem. Catherine's grandma, Evelyn, leaves her a bequest of $80,000 in a trust fund. Catherine will be 21 in 5 years when she can withdraw money from her trust fund. She would like to set herself up for life by buying a chicken farm, which costs $150,000. What return should her trust fund provide to enable her to realize her dream? Right? So we know she has $80,000. She wants to put it in the bank account and get that, and have $150,000 later. So that $150,000 is future value, $80,000 is present value, right? She's got 5 years between now and when she becomes 21. She's got 5 years. So the question is, at what interest rate does she need to earn on her money so that her $80,000 becomes $150,000 after 5 years, right? So we get the present value $80,000, future value $150,000. Is, and we got to find I, right? And of course, if we work with the original formula where future value equals present value times 1 plus I raised to the power n, and basically divide both sides with the present value, and then take the nth root of it, and then subtract a 1, You can do that to both sides, and you'll end up with this expression for I. So I is FV, and FV over PV raised to the power of 1 over n. This is taking the nth root minus 1, right? So this is basically what we need to do. So for we need to do FV. Well, first of all, 1 over n is 5, so 1 over 5 is 0.2, right? We can basically get that answer and set it aside. It's 0.2. But then we need 150,000, that's future value, divided by present value, divided by 80,000, equals, it's 1.875. I want to raise it, y to the power x, to the 1 over n, which was 0.2. And I get this 1.1339665. Then I subtract the 1 over here, and I get 0.133966, or 0.1340, which is 13.40%, right? Of course, I can also use the time value of money functions. And this particular time, because we have a present value and we have a future value, we need to make sure that we are keeping the signage of cash flows correct. So she's got $80,000. She needs to set that aside, right? So that's a cash outflow, and we can say, let's make it then, 80,000. Let's make it negative using the plus minus key at the bottom of the calculator. And a negative 80,000 is present value. Then 150,000 positive is future value. 5 is n. Then compute I by y. Now we get our answer. Remember, in this mode, we get it in the I by y in percent, which is 13.3966, or 13.4%, right? Which was our answer. So it's simpler to calculate using the TVM functions, but we have to be careful that we use the right signage. This sign for present value is negative 80,000, right? In this case. All right, so moving on to the next one. Let's look at this. Bubba Smith has his heart set on a pair of snakeskin boots. The boots cost $600 and Bubba only has $400 in his possession. Assuming that the price of boots remained the same, how long would it take Bubba to be able to afford those boots if he can invest his money at 8%? Right? So what do we have now? We have the present value, which is $400. Future value is going to be $600. Right? The interest rate is 8%. How long will it take? So we have a missing n, and that's what we need to find. All right, so if we work, again, this time we have n as the exponent in this equation. So in order to bring down an exponent, we need to take logs of both sides. And if we complete the algebra, we'll see that n equals log of FVN over PVN divided by log of 1 plus I. So FV is 600 by 400, which is going to be 1.5. So we need log of 1.5. And then 1 plus the interest rate, 1 plus the interest rate is 0.08. So we need the log of 1.08. And we need to divide log of 1.5 with log of 1.08 to get the answer. Right. So now, let's go to the calculator. How we do that? Well, first do 600 by 500. equals, and get that, whoops, I'm sorry, 600 by 400. So it's 600 divided by 400 equals 1.5. And I need the log of 1.5. Well, in this calculator, there's a natural log function. It doesn't matter. You could use log base 10 if you are using another calculator, but make sure that you use the same log for both the numerator and denominator. So we're using natural log. That's because we have a key for that. So natural log of 1.5, and that's this 0.40546. And what I need to do is save this number because I'm going to need it later, right? So you can save numbers by using STO for store, and 1, right? So what I've done is stored this number in one of the memory cells in the calculator. If I do the STO2, I could save another number in STO2 and STO3. And then I can get those back by pushing the recall button. So RCL1 would bring this back. All right, now I need to get the log of 1 plus 0.08 or 1.08, push the ln key, and let's store it STO2. So store that in the second memory cell. So just recall the first one, because that's the numerator, right? We have to divide log of 1.5 with log of 1.08. So that's the numerator. We just recall divided by recall 2 equals. Now we got our answer, which is 5.268 or approximately 5.27 years, right? Of course, we can use the TVM worksheet for this. So do second FV to clear TVM. We are going to need to make sure that we have the right signage. So 400, we're going to set that aside, putting it in a bank account. It's cash outflow. Present value is negative 400, right? And then 600, we will receive that later, so that's future value. 8 is the interest rate I by Y. Compute N, and we get our answer, right? So you can start to see our life has become a lot simpler because we have this little financial calculator in our present. And it gets even better as we go along. So now rather than talking about single cash flows, we're going to start to learn how to handle multiple cash flows, right? Well, not yet. In this one, we actually are going to figure out what to do if interest is paid quarterly instead of annually, right? So Cooter Industries obtains $100,000 loan at 8% interest compounded quarterly. If no intermediate loan payments have been made, how much does Cooter owe after 2 years, right? So what happens is that the law requires all interest rates to be quoted on an annual basis, right? But in many cases, we just get the nominal rate quoted to us. Nominal rate means that we're talking about quarterly interest rate of 2%. And because there are 4 quarters in a year, we simply take the 2 and multiply it with 4, and we get 8. And that's the interest rate that is quoted, right? And the reality is that it's not quite the same. We'll also talk about that issue in a little bit, right? It's not quite the same because what happens is if you are going to have to pay interest of 8% per year, then you could wait until the end of the year and give $8 and $100, right? Or $8,000 on this $100,000 loan. 8% is $8,000, and you can just wait till the end of the year. But that's not how this works. This one is you pay 2% every quarter. So the first $2,000 is due in 3 months. You don't get to wait till the end of the year. So, you know, so that's why 2% per quarter is not quite the same as 8% per year. But that's how interest rates are quoted on a nominal basis, right? So we'll make adjustments for that. So when the stated interest rate is unqualified, when it's not characterized in the statement, then we should assume that it's a nominal rate. So 8% annual rate amounts to a quarterly rate of 8 divided by 4, which is because there are 4 quarters in a year. That equals 2%. The time period, 2 years, equals 2 times 4, or 8 quarters, right? So if we have a quarterly interest rate, we should also have the n, or the time period, expressed in quarters, right? So the amount owed then is the future value after 8 years, which is going to be 1 plus 2% per quarter of 1.02 raised to the power 8, because there are 8 quarters in 2 years. That rate, and multiplied with the original $100,000 loan principal amount, the present value, and we get 117,165.94, right? So what we are doing here is we're taking 1.02 y to the power x 8 equals times 100,000. That's the future value. Using the TVM functions, we'll do second FV. 100,000 is PV, 2 is I, 8 is N, and compute FV. Right? Now we get the answer, which is 117,165.94. So that's how we need to adjust interest and the number of periods when we have non-annual payments, when payments are not annual, right? So we'll look at the next one, right? Let's talk about the concept of effective annual rate then, right? Because what's happening is we just saw that 2% per quarter was not quite the same as 8% per year, right? And you can actually check it by doing 100,000 times 1. First do 1.08, 8% per year, raised to the power 2, multiplied with 100,000, and you'll see that the answer you get will be different from what we just got the prior problem, right? So the effective rate is actually different from the quoted rate, which is also called the APR, right? But EAR, we're going to be talking about effective annual rate. Here's a question. When quoted rate is 12%, what is the effective annual rate with quarterly, monthly, and daily compounding? Once again, we should assume that the quoted rate is a nominal rate. So a 12% annual rate amounts to 12 divided by 4, or 3% quarterly rate, right? Or 12 by 12 months in a year, or 1% is the monthly rate, etc. And then the effective annual rate, you can calculate that by taking the periodic rate, like 3% per year, adding it to 1, so we'll have 1.03 with the quarterly, and there are 4 quarters in a year, so we'll raise that to the power of 4 and then subtract a 1, right? Therefore, well, here are some answers. If the quoted rate is 12%, then the effective annual rate will be, if you take 12 divided by 4, you get 3, then 1 plus 0.03 raised to the power 4 quarters in a year, minus 1 equals 0.1255 or 12.55%. Right? So let's get some of these answers here. Clear TVM or clear work. We're going to do, if we have 12% quoted rate on a quarterly basis, it's 12 divided by, so you can just do 0.12 divided by 4 quarters gives us 0.03. Add that to the, add 1 to it, equals 1.03. Y to the power x, 4 quarters in a year, 4 minus 1 equals 0.1255. Right, that's our answer, 0.1255 in the first instance. If we are talking about monthly compounding, right, then the 0.12 or 12% is divide that by 12, and you get 0.01 as, or 1% is the monthly rate. Add a 1 to it, and then y to the power x, raise it to the power of 12, and you get 0.1268. Well, let's subtract a 1, and then you get 0.126825. So you get 0.1268. Right? What if we're talking about daily compounding? Well, then you take the interest rate 0.12 divided by 365 days in a year, plus add 1 to it, y to the power x, raise it to the power of 365 equals, and we get, and then subtract a 1, and we have 0.12747, or about 0.1275, or about 12.75%, right? So those are the effective rates. And of course, what, as you can see, the effective rate actually is greater than 12%, right? Even though the quota rate is 12%. So effective rate will be 12% only if the interest was charged annually. But if it's charged quarterly, then the effective rate is 12.55%, right? If it's charged monthly, then it's 12.68%. And so, as you can see, the effective rate actually rises as the frequency of compounding increases. And as a matter of fact, if we have continuous compounding, if we were to break down the year into infinite number of periods, then we're not actually distinguishing one point in time from another. It's just a continuum, and with continuous compounding, the answer, the effective rate, is simply e to the power of the interest rate. In other words, if we have a e to the power x button right here, it's above ln, above natural log, and we get to that by pushing second and ln, right? So if you do 0.12 and then second and ln, so we got, now we have e to the power of 0.12, then subtract 1, and you get 0.12749. That's pretty close to what we had before. If we round it up to 4 decimal places, it rounds up to exactly the same as with 365-day compounding. Right? Now, your calculator does have a function that converts APR to ER, or nominal rate, into effective rates, right? And that's here under ICONV, iConvert, which is second and 2, right? And when you do that, it's asking for a nominal rate, and you say that the nominal rate is 12, push 12, and then enter, and down arrow. It's looking at effective, but you need to go down and get, let's say there's we're going to do daily compounding with 365 days in a year, right? I hit enter, and then if I go up to effective and hit compute, I get the answer, which is 12.7476, the answer we had before, right? Now, and that's this answer. I can go up and for change the C by Y to 12 to say for compounding a monthly, only 12 times a year within a year. Enter 12 and go to effective and hit compute, and you'll get the 12.68, which was the answer here. Right? Likewise, if you changed C by Y to 4, enter, go back to effective and hit compute, you'll get the 12.55, which we had before. Okay. And to then exit this, we do second compute. One thing I just remembered is that you may be looking at a brand new calculator in your hand, and it's rounding up everything to 2 decimal places, and you don't want that to happen. So what you need to do is change the decimal key, the format. So it's the key is the format key is second, and this decimal at the bottom, second decimal, and you're going to see the new calculator says DC equals 2. You want to change that to 9. 9 will make it free floating. It doesn't fix 9 decimal places, it just makes it free floating. So push 9 and then hit enter, and then second compute to get out of that, and now your calculator will not be rounding things to 2 decimal places. All right, so there we go. Let's move on from here to the rule of 72, okay? And it's really just a rule of thumb that gives us rough answers, like approximate answers. Approximately, how long does it take to double your money if you can get 5% interest on your money? And to get that answer, you simply take the number 72 and divide it by 5, right? And you get an approximate answer. But you can do it with the number of years too and find the interest rate. For instance, so approximately what annual compound rate would allow you to double your money in 10 years? Take 72 and divide it by 10, and you get 7.2. That's the approximate percent, right? So this applies to doubling your money. It is a rough estimate, right? So the first one says, if you get 5% interest, how long does it take to double your money? Well, let's just do 72 divided by 5, and we get 14.4. Okay. I don't need to show you how to do this in the calculator. I think you can do this, right? 72 divided by 5. And if you do 72 divided by 10, the second part of the question was, at what interest rate will your money double in 10 years? Well, the answer comes out to be 7.2%. All right. And of course, the actual answers will be 14.21 years instead of 14.4, and 7.18 instead of 7.2. That second one's pretty close, isn't it? But how do you find the exact answer? Well, exact answer is just remember what we're talking about. We're talking about if you put $1 away into the bank, so make it a negative second FV to clear it, then -1 is PV, and 2 will be future value, right? Because we're talking about doubling your money. So you set aside $1 in bank, and then you're able to withdraw 2 afterwards. And then if 10 is the number of years, then we'll compute I. Now we get 7.177. That's the 7.18 is a rounding up of 7.177, right? Now let's do this again. Second FV to clear TVM. Now 1 negative is present value, 2 is future value, and if 5 is the interest rate, 5 is I by Y, and compute N, and we get 14.206 or about 14.21 years, right? So those are the exact answers. But you can see that the approximate answers are pretty close using the rule of 72. But that's a quick rule of thumb that you can sometimes use to get a quick answer, especially if you don't have a calculator with you. Right? All right, let's go to the next one. Right? This time we're going to be looking at multiple cash flows. Right? So far, so let's look at this question. Wild West Traders Incorporated finds that Tweedledee thumb twiddlers have turned out to be a more popular product than they had ever imagined. As a result, they will sell the entire stock of 10,000 thumb twiddlers over the next 2 years. And they expect to sell 6,000 twiddlers for $5 each by the end of this year, and the remaining 4,000 twiddlers by the end of next year for $6 each. Right. For budgeting purposes, they will assume that all sales are made at the end of the year. If the relevant discount rate is 5%, what is the present value of these sales? Right. So what we have is two cash flows. Right. After 1 year, you get 6,000 times 5, or 30,000, and after 2 years, 4,000 times 6, which is 24,000. Right? And what's the present value of both of those? Well, the simplest way to tackle this is to calculate present values of the two cash flows individually and just simply adding them up. Right? So what we're doing is we got those two cash flows, and the present value of the first one is 30,000 divided by 1 plus the interest rate 0.05 raised to the power of 1. And the second cash flow, 24,000 divided by 1.05 raised to the power of 2. Right? And then we'll get two numbers. We add them up. We get 50,340.14. Of course, you can use your financial calculator to get those two numbers as well, right? So we do second FV. Let's say 30,000. 30,000 is future value, and 1 is N, and 5 is I by Y. Compute PV. I get 28,571. It'll get this number, and it comes out in a negative, as a negative number for obvious reasons, because I put the FV as a positive. I'm going to store it, but I'll first turn it into a positive number and then store STO1, store that number. Then you have 24,000. 24,000 is the second FV. Oh, I need to do second FV to clear it. Okay, now 24,000 is FV, and 2 is N. 5 is I by Y. Compute PV, and I get the present value of that 24,000. I'll turn that into a positive number, store second. Anyways, I didn't need to actually store it because I just need to add to this the number I'd stored before, recall 1, and get the answer of 50,340.14, right? So what we really just did was treat these two cash flows individually, calculated the present values individually, and we added them up. And that's the present value of the series of cash flows, right? With multiple cash flows. Okay, but there's a certain kind of multiple cash flow scheme that actually is can be handled in one step, right? And here's an example of that. Eliza approaches Scrawny Squirrel with a novel suggestion. Instead of saving walnuts for the winter in this hollow with no interest return, Scrawny can save his assets with Eliza's Nuts and Bolts Bank and earn a return of 1% per month. If Scrawny needs 30 walnuts per month to survive the 6 months of winter, how many walnuts must he save with Eliza before winter approaches? Right? So what do we have? Well, we have 30 as basically there's going to be 30 walnuts per month for 6 months. So we have six payments of 30 each, right? And they occur at the they occur every month. So it's like a monthly series. So if we have a series of cash flows that you know occur at equal intervals in time, and they're all equal in amount as well, and for a finite period of time, we call that an annuity, right? And an annuity doesn't imply that that payments should be annual only. They just have to be periodic, and there should be equal amount of time between payments, and then they and all the payments are the same, as was the case in this particular case, right? So what we're talking about right now is actually the present value of an annuity, the present value of these 6 payments of $30 each that happen every month. And even though some months have 30 days, some have 31 days, and some have 28 days, we will just assume that the time that elapses between the first payment and the second is the same as the one between second and third, right? So the payments are occurring at equal intervals in time, and they're all the same amount, right? So this is a special case of multiple cash flow scheme, where all payments are equal, they occur at equal intervals of time, and they last for a finite number of periods. Such a payment scheme is called an annuity, right? And the people in the past have worked out formulas, simple formulas that can be used for present value and future value of these types of payments as well, right? We are going to need to find the present value of this annuity, which has 30. The amount is 30 every month. There's 6 months, and the rate of interest being paid is 1% per month. Right? Let's go back and look at so we get 1% per month. That's the rate of interest, right? 6 months of 30 walnuts per month. And how much does he need to have in the bank right now? So that makes it the present value. Well, the present value of annuity, the formula for that is simply the $30 a payment times 1 minus 1 over 1 plus I raised to the power n divided by I, right? And that's the present value of an annuity. And so we got, basically, we're going to use the calculator. If it was without the financial functions, what would we need to do? Well, basically we need to have some sort of a plan. I see the most complex operation right here, 1 over 1 plus I raised to the power n. Right, so I'm going to attack that first. 1 plus I is 1%. So 1 plus I is 1.01, and n is 6. So I would do 1.01 y to the power x 6 equals, now I need the reciprocal of that, so there's a 1 over x button, right? And 1 over x, that's 0.942. I need to subtract it from 1, so I make the sign negative and then plus 1, and I get that. So that's the numerator. I need to take all of this and divide it by I, divided by 0.01. Right? I get 5.7954, and then when I multiply this with 30, I get 173.86, right? So basically, that's the answer, 173.86. Let's approximate that to 174, because I don't think the bank is going to accept walnut with a bite in it, So anyways, that's 174. That must be in the bank at the beginning, so that he can withdraw 30 every month over 6 months. That's the present value. What else? Oh, I wanted to also tell you that this 5.7955, which is the answer to this part, right, is also called the present value of annuity factor. And sometimes you can actually Google PVA, present value of annuity tables, and you will see these numbers given to you, right? So a table will have, say, 1%, a column for 1%, and you can go down rows for 6, n is 6, and you will find this number in that table, and in that right cell, the cell that represents 1% columns and 6 years. Of course, you would be glad to know that you can do this easily with the financial functions. Do second FV. We need 30. 30 is PMT, right? 1 is I. Interest rate is 1%. 6 is N. Compute PV. And that's the 173.86 is the answer we had before. And it's so much simpler using the financial calculator, isn't it? And it saves you a bunch of time and hassle. So I think by now you should be convinced that if you're not using a financial calculator, that you should get one. It's very, very handy. Okay, let's look at this one. Mr. Goober invests $90,000 in Prize Fighting Chipmunk Incorporated. Mr. Five, the CEO of the company and himself a champion breeder of prize fighting chipmunks, assures Mr. Goober that his investment will earn him a return of 15% per year for the next 20 years. Mr. Goober's principal and interest will be returned to him in equal annual installments over the period of 20 years. And what's the annual payment that Goober will receive over this period, right? So this is an annuity problem because it mentioned equal annual payments, right? The given value is $90,000 is present value, 15% is I, and is 20. You got to find payment, right? And of course, we already knew present value of annuity was payment times this factor. So the payment is the present value divided by that factor, right? And of course, you can crunch it out, but why? Why should we go through this process when we can simply use our handy dandy fancy schmancy calculator, right? So do second FV to clear this what we had before. 90,000 is present value, right? 15 is I, 20 is N, and we say compute PMT. That's it. We get this answer, which would have required a lot of computation if we didn't use our financial calculator function. Of course, it comes out as a negative number, saying that if the 90,000 positive, that'll be negative. In other words, if you took out 90,000, then that's how much you would have to pay every year for the next 15 years. But the answer is 14,378.53, right? Then go on to the next problem. Well, we're repeating the same one. Bubba Gump Incorporated must acquire a new shrimping boat in 5 years to replace its aging boat currently in operation. Forrest, the CEO, believes that the company can set aside $40,000 per year from its earnings to meet this objective. If the money set aside can be invested at the rate of 11%, how much will Bubba Gump have in 5 years for a new shrimping boat? Right. So this time we're actually talking about an annuity, of course, where we have 40,000 every year, right, per year for 5 years. But we want to find out what would be the value of it this after 5 years. So it's future value. Now, for an annuity, when we talk about future value, we're talking about future value at the end when the payments stop, right? So in this is a 5-year annuity, and so the future value of this annuity can be calculated using another formula where we take the payment and multiply it with this factor. So once again, this is a future value of annuity factor. It looks much simpler. It's 1 plus I raised to the power n minus 1 divided by I, right? So we can basically, if we wanted to use the factor, we would do 1 plus I. I is 11%, so 1 plus 0.11, so 1.11 raised to the power of y to the power x, 5 minus 1 equals divided by 0.11, and we get the factor, which is 6.2278. It's a factor, and then multiply it with 40,000. And you get the answer, 249,112.06, 0.056 rounded up to 2 decimal places, 0.06. And of course, you can simply use the financial functions where you say 40,000 is the payment, 5 is n, 11 is I by y, and compute future value. And it's $249,112.06, right? So basically, at this interest rate, 11%, Bubba will have almost $250,000 at the end. For his shrimping boat. Okay. To go through this to get to the next one. So anyways. All right, let's look at, well, something you might see, come across while, say, you go to buying a car. So Potbelly, a Pontiac dealer, gives you a choice between 4.9% financing or $500 cash back and 6.5% financing on a $22,000 Firebird. In either case, you intend to finance the car for 48 months and you must make a down payment of $1,000. So which of these options should you choose, right? Assume for once that you're a sound mind. Anyways, basically, here are the choices. You get, you're borrowing for 48 months, and the first choice says the interest rate will be 4.9%, right? Well, the second choice says, well, the interest rate will be 6.5%, but you get $500 cash back. Now, first thing we must note is that these are just interest rates thrown at us without a qualifier, so we must know that these are quoted annual rates or APRs, whereas the payments on the car is going to be made on a monthly basis. So we should convert those to monthly rates just by dividing this by 12. And dividing this by 12, we'll get monthly rates. All right. Secondly, what do we do about the cashback option? In both cases, there was a down payment of $1,000. So even though it was a $22,000 car, you only borrowed $21,000 because you put down payment of $1,000. But in the second option, you're also getting another $500 back. What do you do with it? Well, the easiest way to handle that is to use that $500 to increase your down payment. So in essence, rather than borrowing $21,000, you only borrowed 20,500. Okay. Now you could literally not do that. You could take the 500 and spend it, but that's an opportunity cost. So basically, that means um, you by giving up the opportunity of increasing your down payment, you took out that loan at $500 loan at 6.5% financing. So in either case, the answer that we are going to get will come out to be equivalent, right? And let's just then, for the sake of simplicity, use the $500 to increase the down payment. And so in option one, you're borrowing $21,000. Interest rate is 4.9%. In option two, you're borrowing 6.5%. I'm sorry, $20,500 at the interest rate of 6.5%, right? So we can use our financial calculator, and here's the inputs. The first option is 21,000 present value, N is 48, I is, well, remember that 4.9% is 12 annual rate. It's a quoted rate, so we gotta assume it's annual. Divide that by 12, and we get the monthly rate. And then we want to find the payment. When we calculate payment, we get 482.66. In the second case, the PV is 20,500, right? That's the amount borrowed, and it's still 48. I is 6.5 by 12, and when we calculate the payment, we get 48.16, right? And 486.16 rather. So when we compare the two, well, in both cases we have 48 months of payment, but in option one it is a lower payment, right, than in option two. And so because in both cases we're making 48 monthly payments, then we can simply pick the one with the lower payment. And so what happens in the end? In both cases, you come home with the car, right? You went to the dealership with the $1,000, you came home with the car, and you're making 48 monthly payments. And with option one, those payments are going to be lower. So that should be the choice, right? And of course, we did these calculations using the TVM worksheet, where we said, what if the present value is 21,000 and the interest rate is 4.9 divided by 12 equals, that's the I by Y, 48 is N, and compute PMT to get 482.66, right? Then do second FV, and 20,500 is PV, 48 is N, and then 6.5 divided by 12 equals, here that's your monthly interest rate, so I by Y, $48,000. I don't know if I put it in, but just to be sure, I'd put it in again. And now compute PMT, and we get 486.156, so 486.16 if we round it to two decimal places, right? And so those are our answers. Of course, we already know that option one is better. Okay, well, this is gonna be where we stop this lecture. Of course, there's a second part to the same topic that's coming up soon. These lectures were getting to be too long, so I broke them into two parts. I'll be back with the second